Okay, then we'll start with the problems now. So you can read the first question. So there is a long solenoid. Yeah, you have any question here? Okay. There is a long solenoid having a length of 5 centimeter, carrying a current of 2 amperes and 100 number of turns is located along the z-axis. Then determine the magnetomotive force and the magnetic field intensity inside the solenoid. So there is a solenoid, so carrying a current of 2 ampere. You can say I is equal to 2 ampere, and the number of windings is equal to 100 turns, right? So it is located along the z-axis. Then first calculate the magnetomotive force. So we know that the magnetomotive force is straight away. You can define it in a different fashion. Magnetomotive force is nothing but the number of windings into the current per each turn. So in this case, the number of windings is 100 and the current per each turn is equal to 2 amperes. So we can say the value will be 200 ampere turns. Ideally speaking, it is 200 ampere. Turn is having no significance, but I said in the previous class, if you see the textbooks and all, because N is included, they will return that turns. 200 ampere turns is the magnetomotive force. And what will be the magnetic field intensity inside the solenoid? So what is the formula given? Can anybody say? In case of a solenoid, what is the magnetic field intensity? Good, Ni by L, very good. So if you are taking an integration from A to B, you can see here. If you don't remember also, you can straight away follow the approach. So let us say you are integrating from A to B, whose length is D. So what is the closed line integral says? Integral h dot dl is equal to I enclosed. If you don't remember the formula, you follow the conventional approach. And then you are integrating from 0 to D, where D is the length of the solenoid. So from here to here, the length will be equal to D. And the total enclosure current is nothing but your MMF itself, N into I. Right. So what you are going to get, H into D is equal to Ni. So magnetic field intensity H is equal to Ni by D. So same thing, Ni is nothing but 200 ampere turns, you are already got. And length of the solenoid is 5 centimeter. So that is 5 into 10 power minus 2. So what you are going to get, 40 into 10 power 2. So you can say 4 kilo ampere per meter. 4 into 10 power 3. So that I can call it as a kilo amperes. So any doubts in this question you can ask now. So is it clear now? Yeah, see the next question then. So find the inductance of a solenoid having an area of cross section 10 centimeters square and a length of 0.1 centimeter. And given mu r is equal to 2 and the number of windings is equal to 25 turns. So then you find the inductance of the solenoid. So this is straight away the formula based questions. So in our discussion, what we have arrived at the equation of the inductance. So the equation of the inductance is equal to N square mu A divided by D. If anybody didn't remember, you go through the theory part. So then you can see here, the inductance is N square mu A by D. So all the values are given. So you can substitute and tell me the answer. So you can substitute all the values and you can post the answers in the message box. And one more thing, did you remember what is this area represents? When you are taking a solenoid, this area represents, is it the cross-sectional area or the surface area? Cross-sectional area. Good. Yes. So because the flux is there in the upward direction, you should take the cross-sectional area. So that's the reason why I have given cross-sectional area is 10 centimeters square. You can straight away take that. So you can substitute the values. So the inductance is equal to N square is 25 into 25, 1.25 K. So let me solve. So and mu will be mu naught into mu r. So you can substitute 4 pi 10 power minus 7 into mu r is 2 into area of the cross section 10 centimeters square. 10 into 10 power minus 2 whole square. So which is 10 power minus 4. So 1 centimeter is 10 power minus 2 whole square is 10 power minus 4 divided by, so the length of the solenoid is 0.1 centimeter into 10 power minus 2. So you can simplify that. So what value you are going to get, you tell me. So you can use the calculators. So I was getting 1.57 millihenry, correct? Yes, 1.57 millihenry. You can cross check it. No problem. Calculation mistakes and all it will happen, but you should take care regarding the units and all. That's it. So the total inductance you are going to get 1.57 millihenry. Okay, you can verify the calculation part later. Okay, we'll go to the next question then. So see the next one. So there is a magnetic circuit with a small air gap as shown in the figure. The core dimensions are given by, this is the area of cross section of the core. Okay, 1.8 into 10 power minus 3. And the mean core length is 0.6 meter. So what do you mean by mean core length here? Can you tell me? What is the mean core length? Is it represents only this dimension or only this dimension? So the mean core length in this case is nothing but the total length in which the magnetic flux is passing inside the core. So I given the value of mean core length is 0.6 meter. So which is nothing but the distance from here to here and again coming back here. And again also the same way, the distance from here to here. So whatever the length in which the magnetic flux is flowing inside the core is everything together I given it as 0.6. Okay. And the air gap length is given as 2.3 into 10 power minus 3. So you can see here this is the air gap length and the number of windings is equal to 83. Okay. And assume the core is having infinite permeability. So relative permeability will be infinite for that and neglect the effect of fringing fields at the air gap. So as I said in the previous class, whenever the flux is leaving this core, it is trying to expand out. So that is called the fringing effects. So when you are assuming that there is no fringing effect, so there is no leakage of the flux at this junction. So the flux is uniformly flowing through the core as well as the air. Then first calculate the reluctance of the core and the air gap. And the next question, for the current of 1.5 ampere, calculate the flux per each turn. Then calculate the flux linkage and calculate the inductance. Okay. So the first thing, uh, if you want to calculate the reluctance formula, you can remember the reluctance of anything will be given as the mean length divided by mu into area of cross section, right? First case. So if you want to calculate what is the reluctance of the core, so can you post the answer in group? What is the reluctance of the core? Very good. Reluctance of the core is equal to 0 because I given mu is equal to infinity. Right. So because the core is having infinite permeability, the reluctance becomes 0. So in the same manner, find the reluctance of the air gap. So the reluctance of the air gap is nothing but, so you can see here the length is nothing but air gap length. So what is the value I given? 2.3 into 10 power minus 3 divided by, and since it is air, you know the value of mu, that is 4 pi into 10 power minus 7, same as free space, into what is the area of cross section of this air gap. So you can assume that area of the air gap is also same as the area of the core.
1.8 10 to the minus 3.
Yes, you can do that. Then you can calculate and post the answers. So what is the answer you are getting? 1.106 mega ampere per Weber. Good, very good. So you can verify that. So the reluctance of the air will be in terms of 1 point something like 017 into 10 power 6 ampere per Weber. You can cross check that. Okay, once you know the reluctance, you know how to do the total magnetic flux per each turn, right? So that how to do. So you can verify that all of that. I will go to the next one. So reluctance part is over. Then for the current of 1.5 ampere, calculate the flux per each turn. Okay. So if I replace this magnetic circuit with this model, so this is your number of windings into I is your MMF. And this is the reluctance of the core, which is nothing but 0 itself. And this is the reluctance of the air gap. Okay. So when you apply the Ohm's law, what you are going to get? The total MMF is equal to the total flux into reluctance of core plus reluctance of air gap. Okay, then what is the flux per each turn you are going to get now? Ni divided by the reluctance of the air gap. So the flux per each turn is equal to number of windings is 83 and the current given is nothing but 1.5 ampere divided by the reluctance of the air. So you can take the previous one. You got already answer as something like this. So 1.017 into 10 power 6. So you can simplify what is the value you are going to get and you can reply here. So I request everybody to do the calculation so that it becomes a practice for all of you. Okay, you can use the calculators. And once you done with that, you can post the answers in the group. So anybody, what is the flux per each turn you are getting? 0.122 milliwebers. Good, good, right. 1.224 into 10 power minus 4 webers. Right.
Sir, this is like for each turn this flux because we are
Correct.
taking the MMF as Ni.
Yeah, that is a
But
total
like
flux linkage. The next thing. So this is the flux per only one turn, right?
okay, for one because we replace that entire thing with this circuit.
Yeah.
So this is not the entire flux, means it's for
This is
each
not the
turn
entire
only.
flux. This is the flux which is flowing through the loop. You can consider it as only one turn. So the total flux linkage is nothing but n into 5. So the next one is you have to find out that n into 5. Yeah. So next, the total flux linkage, I already told you. It is nothing but the total flux is equal to the number of windings into the flux per each turn. So you can simplify that. So what you are going to get? So number of windings will be 83 and flux per each turn. You already got that value will be 1.224 into 10 power minus 4. So you can simplify that value. 10.76 milliwebers, correct? Yes, you are going to get 1.016 into 10 power minus 2 webers. This is the total flux linkage. And if you are done with that, calculate the inductance also.
Sir,
Yes, yes.
in case of phi total, do we have to mention as turns? Like we mention in case of ampere
In case of
turn?
ampere turn, in this case not required because the flux is always, they will call it as a webers only.
Okay, sir.
Webers, yes. Okay, next thing is the inductance. So the inductance is nothing but, what is the formula for inductance? So the formula for inductance is nothing but the total flux divided by the current. So which is nothing but the flux linkage divided by current. You can substitute that. So the total flux linkage you got 1.016 into 10 power minus 2 by the current passing through that is nothing but same as 1. You can post the answers here now. Good. 6.773 millihenry. Correct. You can verify that. Okay. We'll go to the next problem then. So you consider the same previous circuit only. Okay. The circuit remains same as the previous. Then calculate the number of turns required to achieve a inductance of 12 millihenry. And the next question is, find the inductor current which will result in the flux density of 1 Tesla. So you consider the same specifications as the previous circuit and calculate how many number of windings are required to achieve 12 millihenry inductance. And that find the inductor current which will result in the flux density of 1 Tesla. Can you do that? So first of all, in the previous circuit, once again draw the magnetic circuit model. So what you are going to get, this is your total MMF, this is nothing but Ni, and this is the reluctance of the core, and this is the reluctance of the air gap. So first obtain the equation for the inductance. So what you are going to get, Ni is equal to 5 into the reluctance of the core plus reluctance of the air gap. So reluctance of the core is 0 because infinite permeability. So this is the reluctance of the air gap itself. Okay. Now, then what you need to do in this case right now? So that flux per each turn is equal to Ni divided by the reluctance of the air. 147 is the number of windings. Can you cross check it again? Okay, anyhow, we'll do that. This is the flux per each turn, right? So what is the total flux linkage now? The total flux linkage is N into the flux per each turn. Okay, that is nothing but N into Ni divided by reluctance of the air gap. So what you are going to get? So the total flux is equal divided by I, which is nothing but your inductance, right? So the total flux divided by I is nothing but your inductance, is nothing but N square divided by reluctance of the gap. So you can use this formula now. So you know the value of inductance and find out the number of windings. So if you see the previous case, what is the reluctance of the air gap you got? So that is 1.017 into 10 power 6 ampere per Weber. So you know the inductance and you know the air gap reluctance. Then find the number of windings. So N square is equal to L into the reluctance of the gap. So N is nothing but root over. Inductance value you need to achieve 12 millihenry. And air gap is nothing but 1.017 into 10 power 6. So you can do the calculation now. Yeah, it is 110.47, correct. So the number of windings will be approximately 110. So if you don't know where to start, the simple suggestion in magnetic circuits was draw the magnetic equivalent circuit, then apply the KVL. So automatically we'll come across the method how to do that. Okay. If you're not aware of the startup, where to start and all, first draw the simple magnetic circuit, then apply the KVL. Then you will be able to know the procedure. So then do the second problem now. Find the inductor current which will result in the flux density of 1 Tesla. So what I given, the flux density is nothing but B is equal to 1 Tesla. So you need to find out what will be the value of inductor current to generate the magnetic flux density of 1 Tesla. So since the flux density is given, you can calculate what is the flux per each turn. The flux per each turn is equal to the flux density multiplied with area of the core. Right? Then you can calculate what is the value you are going to get. So in the previous case, I given area of the core is 1.8 into 10 power minus 3, and this is nothing but 1 Tesla. So what is the flux per each turn? So 1.8 into 10 power minus 3 Webers. So this is the flux per each turn. And since you know the value of the inductance here, and you know the flux per each turn, you can calculate the current. Why? Because the total flux you can calculate something like this. The total flux is equal to N into the flux per each turn. Okay, so what is the total? And you know that the total flux is nothing but the inductance into I. So I can say the value of I is equal to N into the flux per each turn divided by L. So all the values are given, you can substitute. So N you are getting it as 110, right? Into the flux per each turn is 1.8 into 10 power minus 3 divided by inductance is 12 millihenry. So you can calculate. So what is the value you are getting? 16.7, correct. You can verify almost 16.5 amperes. Okay, the total magnetic circuit, if you see here, there are four formulas which is revolving around about four things. First thing is MMF. The second thing is the flux per each turn. And the third thing is the total flux, which is nothing but the flux linkage. And the next one is the inductance. That's it. So if you are comfortable with all these four parameters, based upon these four parameters only, you will be able to solve the right. So we'll go to the next one then. For the magnetic circuit shown below, the number of windings is 400 and the mean core length is 50 centimeter and the air gap length is 1 mm. So area of the core and gap he has given, both are same, that is 15 centimeters square. And mu r is equal to 300 for the magnetic core and current is 1 ampere. Then find the flux and flux density in the air gap and the inductance of the coil. So first of all, you can answer me, what is the flux passing through the air gap? Is it same as the flux passing through the core or not? So if you want to find the flux passing through the air gap, does it same as the flux passing through the core or is it different?
Same, sir.
Same, good, because whatever the flux generated here, we have assumed that if there is no fringing effects, the flux will be uniformly flowing through both core as well as the air gap, right? Yeah. So then first you can calculate the reluctance of each core as well as air gap. You can do that. Once you know the reluctance, to calculate the flux, what we can do? The total MMF divided by the total reluctance gives the flux, right? So first start with the reluctance part. So the reluctance of the core is equal to d by mu a. So here the value of d is nothing but mean core length, that is 50 centimeter, into mu is equal to 4 pi 10 power minus 7 into mu r is nothing but 300 here. So the area of cross section or the area of the core 15 centimeter square. So 15 into 10 power minus 4. So you can simplify that. So what is the reluctance of the core you are getting? You can share the answers here. Find the reluctance of the core. Similarly, if you are done with that, find the reluctance of the air gap also. If anybody done, you can post the answers here. 0.88 into 10 power 6. You can cross check it. Some difference is there. Okay, I will write here. You can verify it later. So that will be 88.42 into 10 power 3 ampere turns per Weber. You can cross check that if you are not done with that. And similarly, find the reluctance of the air gap. So the reluctance of the air gap is nothing but same thing, d by mu into a. So this case, the air gap length is 1 mm. So which is nothing but 10 power minus 3 by 4 pi 10 power minus 7 into area remains same, 15 into 10 power minus 4. Okay, anyhow, I was writing the value, you can cross check that. So you are going to get the reluctance will be something like this, 530.515 into 10 power 3 ampere turns per Weber. Okay, then you know the reluctance of the core and the reluctance of the air gap. Some 10 power 3 parameter is missing, you can see that.
So, but still I'm getting as 53.051 into 10 power 3.
No, what is the value of D you have taken? 10 power minus 3?
Yes, sir.
Okay, then you can cross check where it is a mistake.
Yes, sir.
So others cross check that. Is that the value is same or different? If it is wrong, you can correct me. No problem.
Yes, sir, it's 530.51.
10 power 3 is not there. Huh?
It's there, sir.
It's there, right? Okay. Yeah. Then once you know the reluctance of the core and gap, then you calculate the total flux. So calculate the flux per each turn. So what will be the value of flux per each turn? If you are not remember, do with a magnetic circuit. So this is your Ni, and this is your core, and this is your air gap. So what you can say, Ni is equal to the flux per each turn into the overall reluctance, core plus air gap. So the flux per each turn is equal to Ni divided by the overall reluctance. So Ni value is already known. N is 400 and I is equal to 1 ampere. So that is equal to 400 divided by. So reluctance of core plus reluctance of the gap. You can find out that. So we'll get 88.42 into 10 power 3 plus 530.515 into 10 power 3. So we'll get the flux per each turn. So I can simplify. What is the value you are going to get? 0.646 millivebers. Good. 0.6463 into 10 power minus 3 webers. So once you know the flux per each turn, you can calculate the flux density. So can you tell me how to calculate the flux density in the air gap? Switch on your microphone and tell at least one or two people. You know the flux per each turn. You know the flux in this region. What will be the flux density?
Divided by area.
Good, correct. So whatever the flux you got divided with the air gap, because you are calculating the flux density in the air gap. So the flux density is nothing but the flux per each turn divided by the area of the air gap. So the flux per each turn is 0.6463 into 10 power minus 3 divided by, and the area of the gap is nothing but same as the core, 15 into 10 power minus 4. So what is the value you got? 0.43. What is the units? You can verify it is 0.4309 units. You have to be careful. Weber per meter square, right? Not Weber per meter or Tesla. Good. Okay, so the first question is over. You calculated the flux and the flux density. And the next thing is to find the inductance of the coil. So how to find the inductance of the coil? Same thing. So you can apply with the KVL. If you are not aware, you apply with the KVL. So what is that? Ni is equal to 5 into reluctance of the core plus air gap. So the flux per each turn is equal to Ni divided by the overall reluctance, which is sum of core plus air gap. So what is the total flux linkage? Is equal to N into the flux per each turn. Okay, so the total flux linkage, you are going to get N square I divided by the overall reluctance. So in this case, what is the formula you are getting? The total flux divided by the current. Pi divided by I. Yeah, 0.258. Very good. Is equal to N square divided by the overall reluctance. So n square is equal to 400 into 400 divided by, what is the overall reluctance you are getting? So you can see here 88.42 plus 530.515 into 10 power 3. So you can verify that you are going to get 258.52 millihenry. Okay, if you are not done with the calculation part, you can cross check it later, not a problem. So moving on to the next one then. So in a 100 turns coil, if the magnetic flux through each turn is equal to this much Webers, then find the magnitude of the induced EMF in the coil at t is equal to 4 seconds. So this is an application of the Faraday's law, right? At the last we have discussed. So what is the thing I have told? Whenever there is a change of flux with respect to time, you can see here the flux is changing with respect to time. So the change in flux is going to produce the induced EMF in a loop. So if you see the Faraday's law, whatever the induced EMF is, I have given the formula by d phi by dt. So here you have to remember this is the total flux. Okay. So in this case, this is the flux per each turn I have given. So what will be the total flux in that case? The total flux is equal to number of windings into the flux per each turn. So what you are going to get the induced EMF now? Minus n into d by dt of the flux per each turn. Right? So you can substitute everything. So number of windings is equal to 100 into the flux per each turn. I have given it as t cube minus 2t milliweber. So you can consider 10 power minus 3. So you can differentiate that. So minus 100 into 10 power minus 3 into differentiation of this one will be 3t square minus 2. So this is the induced EMF in volt. So if you're done with that, you can post the answer here. 4.6 volt. Yes. So t is equal to 4 seconds, you have to calculate. Substitute t is equal to 4 here. So that will be minus 10 power minus 1 into. So what you are going to get? T is equal to 4 seconds. So 48, 46. So you are going to get 4.6. So since you are asking about the magnitude is always positive, remember. So you have to take the modulus. So the magnitude of induced EMF will be 4.6 volts. Correct. Okay. Now, so this is what the problems actually I planned for the magnetic circuits. So if I summarize it here, all the concepts of the magnetic circuits and Faraday's law together. So it's all about 4 concepts as I mentioned earlier. So the MMF, reluctance, the flux per each turn, and the flux linkage and the inductance. So if still anybody is having the doubt, please go through the previous class. Even I have uploaded the same presentation today. I forgot to upload yesterday. So today morning I have uploaded the presentation. You can go through that and you try to understand all those 5 concepts. Then you will be able to solve the problems. Okay. So any questions you can ask now. So do you have any questions now? So now are you comfortable with problem solving in magnetostatics? Are you comfortable now in the magnetostatics part, especially magnetic circuits? Even actually, what is the thing I would like to clarify it here? Even if you compare the other coaching institutions, they will never dare to touch the topic magnetic circuits. The reason because the magnetic circuits, it looks to be very complicated for everybody. But the actual fact is not like that. If you are really interested, this subject, I told you, right? This subject is very interesting. So you ask all of your friends who is going to the other institutes, they will never touch this. Rather than that, they will simply say the problem formulas and ask the students to remember. But I felt that is not the correct way. So that is the reason why I have taken this whole magnetic circuits, and then I always used to say for all the batches. So the thing is, you should not scold me the moment once you completed the subject, right? So I should be make you that whatever the concepts is available, everything should be clear for you. Okay, then we'll see the revision part then. Shall we start the problems then? So we'll see some practice problems throughout the electromagnetics as well as the magnetostatics. All together we'll see together now. So let's start with some simple practice problem. So the thing is, I'm not going to do anything. So if you are giving up, then I will be able to explain. Okay. Just I was going to tell you the approach in this practice problem. So the thing is, everything you have to do and share the answers in the group. That's it. That is the method. So see the first question. Which of the magnetic fields can exist? So I have given the flux density in the options. At least any person can switch on your microphone and tell me how to solve this problem. You just tell me the approach or the flow chart. How to go ahead. How will you verify whether the magnetic field can exist or not if you know the magnetic flux density? Anybody?
Sir, by checking the divergence.
Yeah, what should be the divergence value?
Sir, grad dot v equals to 0.
Yeah, for magnetic field, if it is existing, you have to, that the Maxwell equation says divergence of B is equal to 0. That's it. So verify which of the option is satisfying, the divergence will be 0. Good. So verify which option is satisfying, the divergence will be equal to 0. So first you calculate the divergence for option A. Is it coming 0 or not? So first one, if you are calculating the divergence, it is simply the differentiation of Ax coefficient. So if you are differentiating e power minus y square with respect to x, you will always get 0 because there is no x term. So do it for B, C and D also, which should come non-zero. Then only you can say option A is concluded. So if one option is satisfying, you can say this one. Right now in your current exam pattern, you have to be careful, right? There are more than one options can be correct. Multiple select questions. So in that case, you should be able to do it for all the cases now. But you need not to do fully. I will tell you the simple short how to eliminate. You can see here. So since if you are differentiating the second one, I mean differentiation of e power minus x square with respect to x, you are going to get finite value because this is also the function of x. So in that way, you can eliminate that. You don't differentiate it. So differentiation of Ax coefficient is a function of x. So when you are taking the divergence, it will be non-zero. Same manner, here you can see there is a AR coefficient and a sin kr, which is also the function of r. So when you are differentiating the AR coefficient, you will obviously get the same thing, which is a non-zero quantity in a spherical. So similarly, what about this one then? R into a theta cap. So since it is a theta and coefficient is r, can you say the divergence of B will be 0 in this case? Is it yes or no? Yes. Yes, no, mixed answers. So when you are going for the spherical systems, you have to be more careful with the scaling factors, right? So there will be a scaling factors. So when you are writing the divergent equation in spherical, what is the value? If you remember fully, I have given this equation plus 1 by r sine theta dou by dou theta of sine theta d theta plus 1 by r sine theta dou by dou phi of d phi. So this is the formula, right? So in this case, there is no rho coefficient, there is no phi coefficient. So for the theta coefficient, you should multiply with sine theta. So in that case, what you will get? 1 by r sine theta into dou by dou theta of sine theta into d theta will be r, right? So you are going to get 0 or non-zero now. So r you can take it common and get cancelled. So 1 by sine theta. So dou by dou theta of sine theta will be cos theta. So you are going to get a term which is non-zero. Yes. So the only one which is satisfying the magnetic field is nothing but the option A. So for option A, if you are taking the divergence, which will be 0. Okay, go to the next one. So see the next question and solve this one. So there is a 500 millicoulomb charge is at the center of the square of side 10 centimeter. Then find the work done in moving a charge of 10 millicoulombs between two diagonally opposite points. So there is a square, and at the center of this there is a 500 millicoulomb charge. What is happening here? I think again this. So you can see here there is a 500 millicoulomb charge which is located at the center of the square, and the dimension is 10 centimeter here. Then you need to find out how much work done you have to do in moving a charge of 10 millicoulomb between two diagonally opposite points. So suppose if you say this is the first point A and this is your second point B. I want to move the 10 millicoulomb charge from point A to point B. So what should be the work done I have to do? So you can switch on anybody. What will be the approach you have to do? So you know that in case of electric potential, we know if there is any electric field exists in a medium, and if you want some external work done, okay, so the amount of the work done you have to do will be given by minus qt into E dot dl, right? In other words, I already told you this work done is equal to qt into the potential difference. So when you are integrating from A to B, this is nothing, or B to A. You can move it in either fashion. That is fashion, right? So this will be the potential difference. Agree, right? So the work done you need to do in order to move a charge is nothing but the amount of the test charge multiplied by the potential difference between these two. So can you tell me what is the potential difference between A and B?
0, sir.
0. Good. Why? Because there is a 500 millicoulombs at the center, so it will cause for some potential here. And because this is also at the same distance, you will get the potential at A and potential at B will be same. Because you assume this is your original charge. So what is the potential here? Q by 4 pi epsilon into R. Potential is a scalar. And what is the potential here? Q by 4 pi on into R. Right? Because Q is same and the distance is also same. Potential at point A and point B will be same. So if you are at the same potential, you need not to do any work done, right? So that's what it says. When the potential difference between B, so both are at same potential, the potential difference will be 0. So the work done will be straight away 0. Understood? So is it clear for everyone? Repeat. So which one you want me to repeat? The same thing. Work done is nothing but the charge into the potential difference. The test charge you are moving is of 10 millicoulomb, right? And potential difference at point A and point B. So when you are moving from A to B, what is happening? Again, my presenter status is changing all the time. Okay, when you are moving from point A to point B, what is happening here? Because point A is at the same distance from the source. Point B is also at the same distance from the source, right? So then the potential difference will be 0. Right? See the next problem then. So there is a circular coil of radius 10 centimeter is made up of 100 number of turns. Right? It carries a current of 5 amperes. Then compute the magnetic field intensity at the center of the coil. So do it and tell me the answer now. So first, what is the magnetic field intensity due to a circular coil? Let us see is the current flowing through that and at the center. So what is the magnetic field intensity formula given? You remember? Just before the Helmholtz coil, I have discussed what will be the magnetic field intensity at the center.
I by 2R.
Correct. So this I by 2R is valid by assuming there is only one turn. Right.
Yes.
Right now, in this case, how many number of windings are given? N number of turns. So the magnetic field will be 9, right? Right now, this coil is surrounded by N number of windings. So the total current becomes Ni. That's it. N into I by 2R. So you can calculate that and share the answers. So N is equal to 100 and current is 5 amperes divided by 2 into. So what is the radius you given? 10 into 10 power minus 2. Correct. Option C. So you are going to get 2500 ampere Tesla per meter. Okay, we'll see the next one then. See the next problem. This is the problem on boundary conditions. So the electric field intensity in the medium 1 with epsilon 1 3 epsilon naught is given by this, and the medium 2 is having a different permittivity, and x is equal to 0 is the boundary. Then find the electric field intensity in the second medium. Okay, you can do this and share the answer now, because already we've seen the problem. I don't want to discuss it again now. So you know all the boundary conditions, right? You can go ahead now. So this is equal to x is equal to 0. And you know the electric, let us say this is your medium 1 and this is your medium 2. So all the values are given, you can put that. So epsilon 1 is 3 epsilon naught here. And E1 is nothing but AX cap minus 5 A1. I think something is happening always with mine. Presenter status is going. So then you find the electric field intensity in the medium 2. So the boundary conditions, right? And since in this question regarding the interface he has not given any, you can assume the rho s is equal to 0. So option B, very good. See, since you know the electric field intensity in medium 1, so what will be the tangential component? E tan 1. Because x is equal to 0 is the interface, y and z will be tangentials. So tangential component minus 5 ay cap plus az cap. So this is same as your E tan 2 using the first boundary condition. And if you want to declare the normal component, so we had one more relation, d normal 1 minus d normal 2 is equal to rho s. So in this case, rho s will be 0 straight away. So you can calculate that. So d normal 1 is equal to d normal 2. So epsilon 1 E normal 1 is equal to E normal 2. So then find the value of E normal 2. So epsilon 1 by epsilon 2, that is ratio of 3 by 5. So 3 by 5 into AX cap. So this is nothing but 0.6 AX cap. So finally, what is the sum of total now? So 0.6 AX cap minus 5 AY cap plus AZ cap. So this is your answer. See the next one then. So I think there is some problem with my network. I will close the connection and I will connect it back. Okay.